Okay, welcome back. So I'm going to finish up block ciphers from last time. We might end up a little bit behind, but that's okay. We planned for it, so we should be all right. Okay. So last time we saw the block. Wait, hang on. People in person can't see this. But now they can. Okay. So this is what we saw last time. That was the block cipher. Remember that it took in key and some plain text. The key has to be k bits long. The plain text has to be n bits long. K and n are both fixed. It runs some sort of shuffling on the k and the n input, and then outputs ciphertext. That's one way to look at it. And we saw how you can implement this using something like AES that shuffles all the bits around. Another way to look at this is you can also think of this as like a family of functions. Once you choose a key, it's now a mapping of plain text to ciphertext, where you have all the plain text on one side, all the ciphertext on the other side, and the block cipher encryption function with a certain key as the setting maps all the inputs to one unique output. So that's what we saw from last time. Now, something that people asked last time afterwards, which I figured I should clarify real quick, is that block ciphers have a good security property, which we saw. So that was here. So this was the security definition of block ciphers. And so we said that a block cipher is secure if these arrows are indistinguishable from arrows that you drop at random. So if an attacker cannot tell whether the arrows came from the block cipher with a certain key setting, or if they were just dropped in at random, then we say this block cipher is secure. However, just because a block cipher is secure using this definition, oh, interesting. Speaking language is shiny simplified. Awesome. Okay. So just because the block cipher is secure using this definition does not mean that it's secure using our in-CPA definition. So while this definition of security is a nice building block for making our block cipher secure, it doesn't by itself imply that we have in-CPA security, which is what we ultimately want. So these are two different definitions of security. This tells us whether a block cipher is secure or not using this particular definition. But just because a block cipher satisfies this definition, which is that it behaves like a random permutation, it does not mean that block ciphers actually solve the problem of allowing us to communicate between two parties. The reason why we saw last time is because block ciphers, there's no randomness. If you encrypt the same thing 5 times, you get the same output 5 times. So that's what we're going to spend all of today, or most of today, solving. So we already saw there was one possibility from last time, which is if my message is longer, I could simply use the block cipher twice. We already saw this from last time. This is called ECB mode. We use the same key. We take the message, we split it up into chunks, pass it through the block cipher multiple times, take all the ciphertext, concatenate them together, and we get our final ciphertext. So this works, but it's not in-CPA secure. Why is that? Because we talked about how there's still no randomness. If you encrypt the same thing 10 times, you get the same output 10 times. We saw it with the penguin. If you encrypt this penguin 10 times, you get the same output 10 times. If you use a block cipher that's deterministic, penguin is still visible. So we don't like that. We got to fix it. So let's fix it today. So we've already seen that schemes that are deterministic, they don't work because if you encrypt the same thing twice, you get the same output twice. And by definition, that fails the in-CPA game. The attacker wins that game. The scheme's not secure. So let's fix it. Here's what I'm going to do. I'm going to start introducing randomness into these schemes. And so what I mean by that is I'm going to make it so that if you encrypt the same thing twice, the output looks different each time. That's what I want. So let's try and make that happen. So here I go. I'm going to take some random bits. This initialization vector, that's a fancy term for a bunch of random bits. Okay, so I'm going to pick a bunch of random ones and zeros. I'll flip a bunch of coins, get a bunch of ones and zeros. And here's what I'll decide to do. I'm going to say this plain text, instead of passing it directly through the block cipher encryption, because if I do that, I'll get the same output every single time. I am first going to XOR it with this special initialization vector and then encrypt it. And then the result now is going to be different every time. So if I encrypt the same message twice, I'm going to pick a different set of random bits every single time, XOR it, and then the result is my ciphertext. Okay, so that looks good. I haven't proven to you that you can decrypt this or that this is secure yet, but at least I've done something so that when I encrypt the same thing twice, I don't get the same output twice. Does it totally work? Well, not quite. We have to think about how the decryption works and all that. But I've thrown in some randomness. So, I've taken the first step. Okay, so does this mean that if I encrypt the same thing 10 different times, like if I encrypt the penguin or something, is the penguin going to be completely indistinguishable from random now? Am I all set? Well, let me think about this. Well, if I pass in, some message, remember that the overall message is this entire thing, and I'm splitting it up into chunks. So yeah, even if I pass in the same message twice, this first chunk is going to be different because even if I pass in the same message a second time, it's going to get XORed with a different piece of randomness. And so this piece of ciphertext will look different. Okay, that's great. But what about this one? This is also a part of my message. It's like the middle third of my message. What's happening over here? I'm taking the message, I'm passing it straight through the block cipher encryption. It's the same message. I encrypt it, I get the same output. So this part of the plain text, there's no randomness. If I encrypt the same thing twice, or if I encrypt a message twice, that middle third, it ends up looking the same. And same thing over here at the end. This last block, when I encrypt it, I still get the same ciphertext. So I introduced randomness, but not to the whole thing. So we need to do a little bit better. Let's add some more randomness. Okay. So one thing I could do is I could say, well, maybe I'll throw in some more random values. That's one possibility. But I'm going to do something a little bit smarter. So instead of saying you get a random value and you get a random value, because now I have to come up with all of these different random values, that's a lot to keep track of. I'm going to notice something kind of clever, which is this ciphertext from an attacker's perspective, because this is a message that I'm sending over the insecure channel. From the attacker's perspective, what does the ciphertext look like to them? It looks completely random to the attacker. How do I know that? Because if the attacker doesn't know the key, what do we know about block ciphers? Block ciphers look like a random permutation. So from the attacker's perspective, this ciphertext down here, it might as well be random ones and zeros for them. Okay, so if this is as good as ones and zeros that are completely random for someone who doesn't know the key, then instead of coming up with another initialization vector or another set of randomness, I'm just going to say this thing down here from the attacker's perspective is basically random. So let's just use that instead. So there it is. Instead of passing in a new initialization vector here, or instead of passing in the same one that I was already using, I'm just going to take that ciphertext, which I know the attacker thinks is basically random looking. It's unpredictable. Can't really tell what it means. And I'll use that to introduce randomness into the second block. Okay. Well, that's nice, but still haven't solved the problem of my third block. Third block still looks the same. If I encrypt something, the third block still looks the same one after I encrypt it. Okay, so I'll solve that problem too. I will repeat this over and over again. And every single time I encrypt something, before I encrypt it, I will first XOR it with some randomness and then pass that block into the block cipher encryption and get some output. Okay. So all that I've done is I've decided my original scheme, it was deterministic. I didn't like it. I had to introduce randomness. So this is what I came up. I just came up with some way to stick some randomness into the scheme. I haven't told you that it works yet, but it looks like at least some way to introduce randomness. Okay. So it turns out we invented something new. That's great. So we invented something called CBC mode, stands for Cipher Block Chaining. And you don't have to remember what it stands for, but the chaining comes from the fact that I'm chaining all these blocks together. And so that's nice. So now let's think about, well, we can think about a couple of things. So one of the things we can think about is, what is the encryption equation? Remember, even as we're drawing these pictures, which are nice, ultimately, we can always write these as expressions, like what is the encryption expression? What is the decryption expression, right? So let's do that. So I guess I've already kind of spoiled it here, but we can try to write this too. So we could say, well, first of all, my message is no longer, just one message. I realize that I have to split the message up into a bunch of chunks. That is what I see down here. So the first thing I have to do is I have to say my whole message, it is not just one M, it's like M1, M2, M3. Sometimes people call it P1, P2, P3. That's what this slide says. But the idea is you're taking your message and you're splitting it up into chunks. That's the first thing we have to do. And so I'm going to use subscripts to denote splitting the message up because I cannot encrypt the entire message in one block cipher encryption. I had to divide it up. So let's do it. So I'll say, well, I want to encrypt, let's say, I want to encrypt key message. So the first thing I'm going to do is I'm going to take that message and I'm going to say this message it's really, M1 concatenated with M2, concatenated with M3, and so on. And all that I've done is I've taken the message, I've split it up into chunks, just like you see in the picture. Okay, that's good. And so now, instead of writing the encryption as one single expression, I'm going to write it in terms of those little chunks, because I can look at the picture and know how those chunks work. So I will say, instead of encrypting, I will say encrypt, instead of encrypting the entire M, let's think about how you encrypt a specific block. So let's say, how do you encrypt M sub I? Okay, well, let's see what happens. So suppose this block is the ith block of ciphertext. So what do I do with the ith block of ciphertext? Or the plain text, sorry. I take the plain text, what do? I XOR it with what? Well, I XOR it with the thing from the previous block. What's the thing from the previous block? The thing from the previous block is C of I minus 1. You think down here, I could also name these C1, C2, C3. Okay, so I take my message, I XOR it with the thing from the previous block, and then what? And then I shove it through the block cipher encryption. So I'll write that as E sub K. So now I have my encryption algorithm. And the way that I got it is I looked at the picture, I thought about what the picture is doing to my input, and I wrote it out. Okay. And what's the result? The result is the ith block of ciphertext, which is C sub I. And then ultimately, what do you do with all of your C sub I? You mash them all together. Okay. That's great. So that's our encryption algorithm. You see it there in kind of nicer typesetting than my sloppy handwriting. So that's great. So that's how you encrypt. You split it up. You encrypt each one block by block, but you add this like chaining idea. So we add some randomness overall. Okay. That's great. Now let's ask the question, which is, well, how do you decrypt stuff? So how do I decrypt something? If I give you a piece of ciphertext, how do you decrypt? Well, again, we can look at the picture and we can try and use the picture to reason it out. So there's kind of two ways to come up with your decryption algorithm. One way is I can look at my picture and I can say, okay, this is C sub I, and I want to know what M sub I is. So how would I do that? I need to write an expression for M sub I. So let me try that. M sub I is equal to, well, I know I've got C sub I. What do I do with C sub I? Well, the first thing I should do, according to this picture, I should run it backwards through the block cipher algorithm to decrypt it. So let's give that a shot. We'll say, I will decrypt the ciphertext. I run it backwards, and now I am like at this phase up here. So now what? Well, now I need to get rid of this XOR because I want to go all the way back to M sub I. So I want to cancel out that XOR that I added in earlier. So how do I do that? Well, after I decrypt, I need to cancel out the XOR. What did I XOR it with? I XORed it with, the previous ciphertext. So if I looked at the picture, I could deduce that that's the decryption algorithm. That's one possible way to get it. If you like pictures, that's the method for you. Trace it backwards through the diagram and think about, okay, I have to run it backwards through the block cipher encryption. So I'm decrypting. Then I have to get rid of that XOR, so I cancel it out. What do I cancel out? I cancel out the C of I minus 1. That's one possible way to do it. Another possible way, if you like algebra, big algebra fans, you could say, wait, I have an expression right here that relates M and C. And this gave me C in terms of M. But if I want to decrypt, what I really want is I want M sub I equals something, some expression that tells me how to decrypt. So maybe I'll just do some algebra to solve in terms of M. So I can also take this expression and do some algebra. Hopefully I have it on the slide so I don't have to draw it for you. So we already saw the picture version, which is what you see on this slide. I believe there's an algebra version. Okay, so there is. We have this expression that relates M and C, and I can just run a bunch of algebra steps to solve this thing for M. That's another way to do it. So valid operations are, you can decrypt both sides. That works. And if you're not convinced that it works, think about the fact that it's bijection. And because it's a bijection, decrypting both sides will give you the same result. Okay. Once I decrypt both sides, I realize that if I encrypt something and I decrypt something, what's the definition of a block cipher? Encryption and decryption, they are inverses. So if I encrypt something and decrypt something, that goes away, gives me the line over here. Okay. But still not in terms of M. I want something in terms of M because that tells me how to decrypt. So I realize I want something in terms of M, but there's this pesky term right here that I want to get rid of. So how do I get rid of it? I XOR both sides with C sub I minus 1. Now these cancel thanks to my handy canceling property of XORs. And then finally, I get an expression in terms of M sub I. It's the same expression from before. So I'm all set. So how do you come up with decryption algorithms if you know how to encrypt? You can either stare at the picture, that was this slide. I stare at the picture and think about how do I run the picture backwards? You can even draw the decryption diagram like we did here. That's running the decryption or running the encryption backwards. Take the ciphertext, run it through decryption, right? Run it through decryption, and then XOR it with the previous ciphertext. You can draw it out, or if you like algebra, you can write out the expressions and say, I have something that's C in terms of M. I want something that's M in terms of C. I do a bunch of rearranging. These are all valid operations you can do, and you come up with your decryption algorithm. Okay, before I take questions, one more thing I want to note, which is a pretty common piece of confusion when we see these for the first time, is this initialization vector. This is something that was on the slide, but I haven't called attention to yet. It's part of the ciphertext. And at first you might be like, wait, why is that the case? So there's a couple ways to think about this. Well, one way to think about it is, suppose you just send the ciphertext and you do not send the initialization vector. Well, then if you don't send the initialization vector, if someone receives the ciphertext, how are they going to know how to decrypt it? Well, we can look at the decryption algorithm, but what you'll eventually notice is that if you don't have the randomness that the person introduced while they encrypted the message, you're not going to be able to get the original message back. So that's the intuitive way of thinking of it. We have to include the randomness. We have to include the randomness as part of the ciphertext because whoever is decrypting, they need to know what randomness I introduced in order to like get rid of the randomness and find the initial ciphertext, or sorry, the initial plaintext. That's one way to think about it. If I introduce randomness, the other person has to be able to get rid of it. Another way to convince yourself is to look at the decryption picture or the equation, and you might see over here, how do I arrive at the first block of plaintext? On the right, we have the decryption diagram. Well, the way that I arrive at it, and you can look at these two diagrams and convince yourself, is I have to take the ciphertext, the first block of ciphertext, I have to decrypt it, and then I have to XOR it. XOR it with what? Well, when I encrypt it, I XOR it with the initialization vector. But when I decrypt, I have to cancel that out, and I have to XOR again with the initialization vector to get the original plaintext back. So if you're someone decrypting, you need to know what this value is in order to get the original plaintext back. If you don't, then you're kind of out of luck. Okay. So you can look at the equations, you can look at the picture, you can think about it and realize that if someone introduced randomness into the scheme, they need to also tell you what randomness they introduced, so you can pull out the randomness and get the original message back. Okay, now I can take some questions. Yeah.
Go back to the diagram.
Yeah, diagrams.
If the initialization vector isn't present, we can still decrypt all of the other blocks, right?
Yeah, that's a good question, which is what happens if there's no initialization vector? It is true that you can still decrypt a lot of the other blocks, but the first block would not be decryptable. Okay, other questions? Yeah.
So if you tell them what the initialization vector is, and how do you see that? That's sort of
yeah, that's a great question, which is if you tell the attacker you're passing over the insecure channel that initialization vector, does that defeat the point of randomness? That's a great question. And to answer it, we're going to have to try and reason about the security of this thing, which is hopefully coming up in a slide or two. Okay, so let's do it. Okay, so I guess before we do that, let's just make sure and convince ourselves that this is pretty fast. So we already know that block ciphers, they just do a lot of XORing, bit shifting. Those are all really fast operations, which is great. And if we look at what else we have introduced into the scheme, it's mostly XORs. We introduced a bunch of XORs, so I'm not going to add too much extra time. So we like that. Another thing that's kind of nice is that, well, modern computers, they often don't just execute one thing at a time. They like to execute lots of things in parallel. So say I have a plaintext that's like 1,000 blocks long, 1,000,000 blocks long, 1,000,000,000 blocks long. Could I encrypt each part of the plaintext in parallel? Because that would be nice. I could say, processor 1, you encrypt the first half, and processor 2, get to work on the second half. And that could save me time too. I want encryption to be fast. I want people to use my algorithms, so I want to make them fast. So can I parallelize? Well, if I look at this, say I want to encrypt block 3. So I'm like, processor number 5 or whatever, please encrypt block 3 for me. Well, processor 5 is like, okay, I'm going to start encrypting. So I'm going to take my plaintext. I'm going to XOR it with what? I'm going to XOR it with ciphertext. Uh-oh. I have to wait for whoever came before me to finish their block so that they can give me the ciphertext. I can plug it in and encrypt. So can this thing be parallelized? Well, not really. If I want to encrypt some block, I need to wait for whoever came before me to finish encrypting their block. So I can take their ciphertext, pull it over, and then XOR it with my plaintext. Okay, so I can't parallelize encryption, which is too bad. What about decryption? So decryption, can I say, hey, you encrypt, or you focus on decrypting this, someone on this side of the room, and then someone on this side of the room, please decrypt this. Can you each work on these things separately and then give me the result later? Well, let's look. So let's pick an arbitrary block. There it is. What do I need to be able to decrypt? Well, I need the ciphertext. I have that. The ciphertext is the thing I'm trying to decrypt. I have all the blocks of ciphertext when I start decrypting. That's okay. I can pass through decryption. I can do that myself. That's okay. And then I have to XOR it with something to get the plaintext. What do I have to XOR the ciphertext with to get my plaintext back? I look at the picture, I trace it backwards, and oh, okay, I need to XOR it with the previous ciphertext. Do I have that? Well, yeah, I do. I have all the ciphertext available to me when I am beginning the decryption operation. So if I need to decrypt something, the only things I have to reference are different blocks of the ciphertext, in particular, my own block and the block that came before me. That's it. And because all I have to reference is ciphertext, I can do this without waiting for someone else to finish computing plaintext. Because you can think of this as we split the job up, everyone's busy computing some part of plaintext, but when we're doing the computations, we only have to reference ciphertext. So we can all do this in parallel, and then when we're done, we can combine the plaintext together. So CBC encryption, we can't do that. We have to wait for the previous block to finish encrypting to get the ciphertext out. But CBC decryption, we can do in parallel because everybody only needs to know the ciphertext to compute decryption of a specific part of a message. So that's great. Okay. So we reasoned a little bit about efficiency, in particular, whether or not these things can be parallelized. And by parallelized, we mean, can you split the message up and have one person encrypt one part, one person encrypt the other part? So for encryption, no, you can't. You have to wait for person I to finish before person I+1 can work on block I+1. For decryption, yes, you can parallelize. Okay. Now let's look at, okay, I guess we can't talk about security yet because I have to make sure this thing totally works first. So one thing I'm going to notice is, well, this works great if my messages are exactly a multiple of the block size. So if my message is exactly 1 block long, this works great. If my message is exactly 2 blocks long, it works great. I split it into 2 blocks, I pass it through. Same thing if my message is 3 blocks long. But what if my message was like 2.5 blocks long? Well, let's give that a try. I take my message, which is like 2.5 blocks long. So if my 1 block is like 16 bytes, 2 blocks is 32 bytes, maybe mine is like 40 bytes or something, not a multiple of 16. So I'll take my first block of messages, or my first block of the message, I will stick it right there. Perfect. Then I'm going to keep splitting. I'm going to take my second block, split it up, put it right there. Perfect. What's left? Well, I only have half a block left to go. So I will take my remaining half block and put it right there. Perfect. Or is it? Because now how do I encrypt this thing? Well, let's take a look. I can take this full block of plaintext XOR with my full block IV. That works great. I can encrypt that. That's great. Same thing with the second block. But look over here. If I only have half a block, how am I going to encrypt half a block's worth of material with like the full block of ciphertext? How does that work? And even worse, even if you were to figure that out, even if the result was like half a block long, like what do you pass into block cipher encryption? Remember, that block cipher, it takes in exactly n bits, whatever the block size is. So if the block size is 16 bytes, you must pass in 16 bytes. If you pass in anything less, like 8 or 9 or 10, the block cipher will say, no, I refuse to encrypt this. I don't know how to do it. You need to pass in exactly a multiple of 16 bytes. So we have a problem here because if we only have a half block of message left at the end, we don't know how to pass a half block of a message through a block cipher encryption that's expecting a full block. That's a problem. So how do we fix it? Well, it's not too bad. One way to fix it is to say, you know what? I'm just going to add some extra characters at the end until my message is the right length. So if my message only fills up 2.5 blocks, I will take my message and just add some padding bytes at the end. They could really be anything. And as soon as I add them, now I have a longer message that is a multiple. And because this is a multiple of the block size, it goes right into the block cipher encryption. Okay. So if my message is, like 2 blocks plus another like 8 bytes. I might have to add more bytes of padding until I get a multiple of 16, and then I'm good to go. Okay, that's padding. It's a fancy way of saying adding those bytes at the end. They're not part of my message. I don't actually care about communicating those bytes to the other person, because what I really cared about was my 2.5 blocks of real message. So I'm not adding to my message. I'm just adding bytes for the sole purpose of making sure that I can pass things through these encryption blocks. Okay, so that's padding. And turns out padding is one of those things that's like easier said than done. And you'll get a chance to explore this in homework 3, I believe. And so I'm not going to talk about it too much. You can play with it in homework. But it turns out, if you think of, maybe the first padding scheme that comes to your mind is maybe, you know what, I'll just shove a bunch of zeros at the end. Turns out that doesn't exactly work. Same thing with padding with ones and so on. So you have to be a little bit careful. I'm not going to talk through this entire slide, but you have to be a little bit careful with padding, because whatever you pad, the other person has to be able to remove that pad, chop it off, and get the original message back. And so if you add padding and it becomes ambiguous which parts of the message are padding that you added and which parts of the message were your true original message, then you have a problem. And you'll get a chance to explore this in homework 3. So I'm not going to spend too much time on it, but just know that padding, not every type of padding works. You have to be really careful and make sure that whatever you add as padding, you are able to get rid of it later when the other person decrypts the message. Okay, great. Finally, I can talk about whether this scheme is secure or not. So I will tell you, I will not prove to you. So the proof requires making more assumptions, and not something I have time for right now. But I will tell you that this thing is secure, but you have to make certain assumptions. You have to use it correctly. So what's the assumption? Well, the assumption is that IV that I claim to be random, it better be random in order for this NCPA security to hold. That's one of the requirements for NCPA security to hold on this. And so how do we know that? Well, let's think about what happens if you use the same IV twice. Well, if you use the same IV over and over again, or say something even worse, instead of using the IV, you just say IV equals 5, and you just plug in 5 over and over again, then what are you back to? You're back to your deterministic schemes. And we've already said schemes that are deterministic, they're not secure. Okay, so we already know that in order for this scheme to be secure, whoever is using it had better remember to change the IV up every single time they encrypt a brand new message, because if they encrypt 2 messages with the same IV, then I'm back to deterministic. If the messages are the same, then the output's the same. I'm back to the penguin problem, where the penguin is clearly visible. Okay, that's the problem. So make sure you use different IVs every single time. And intuitively, although we don't really have the tools in this class or the time to prove it in great detail, right? The security proof roughly says, and again, this is not an actual proof, it's like more of a sketch, maybe even less of a sketch. It roughly says, okay, well, we already know that the block cipher outputs are all indistinguishable from random. So that's kind of the property or the building block that I'm using to make this whole scheme secure. So again, we don't really have the tools to prove it, certainly not in like an 80-minute lecture, but the rough idea is that all of these outputs from the attacker's perspective, they're outputs of the block cipher. And we already know that outputs of the block cipher are as good as random. Someone who doesn't know the input of the block cipher and doesn't know the key has no way of knowing what the output of the block cipher is. Or even someone who doesn't know the key, from their perspective, this might as well just be total randomness, right? Okay. So yeah, we don't really have the tools to prove it, but that's kind of the sketch, is that all of these outputs that are falling out of the block cipher, they are indistinguishable from random. And the question of, if you know the randomness, does that break security? Well, we can give it a try. So say you're the attacker, you don't know K because you're the attacker, but you do know the initialization vector. This randomness is public. It has to be public so the person decrypting can get rid of the randomness and go back to the original message. So if you know this, well, what can you really do with it? Well, it's not immediately clear. You can play around with it, think about different strategies, but it turns out that even knowing this, it doesn't help you predict what happens down here. If you don't know the key, you have no way of knowing what the block cipher output is. It's as good as random to you. So knowing the random initialization vector, it doesn't give you any clues as to what the ciphertext output is. Same thing over here. Just because you know that you're plugging in some known ciphertext doesn't help you at all with what this output is. It's basically indistinguishable from random. Okay, to do this formally, you would have to go through and consider like all of the strategies an attacker can use. but we don't really have the tools to do that. Okay, questions? Yeah.
Why, this be honest at this time, but why does it need to be random? Why can't it just be unique?
Yeah, there's a question of, is there a difference here between random and unique? There is a question in, I believe, discussion that will talk about this. So is it enough for this initialization vector to be just unique or changing every single time? I think discussion will talk more about it. There is an attack. It's pretty subtle, so we're not going to talk about it here. But in discussion, you'll get to see an attack where the initialization vector is predictable and that actually causes problems. It's a good question, though. Okay. But if we're paranoid, we know that if it's completely random and unpredictable every single time, things will be okay. Okay. So that's the rough security sketch. Let's talk a little bit more about what happens if you do reuse the IV. So we already know that if you use this thing improperly, if someone gives you the tool and you don't use it correctly, well, we already know that it's not going to hold against our NCPA definition, which means that it's going to leak information. We already know that if you encrypt the same message twice, you're going to get the same output twice. So that's already going to leak information. An attacker could be like, oh, this thing that you sent today, it's the same thing as what you sent last Tuesday. That's not good. That's leaking information. So we don't like it. But it turns out, even if you don't send the same message, things could still go wrong. And so this slide, with all of its fancy colors, is showing you that even if you don't send the same message, IV reuse can still leak information about your message. So let's consider two messages. And this is also a nice time to remind you that having multiple messages is not the same as a message being split into blocks. So I can actually have two messages, which is what I have on this slide, and each message can be multiple blocks long, and I'll split them into blocks. Okay, so this is the first message, it's split into 3 blocks. This is the second message, it's split into 3 blocks. So just so you're aware, having multiple messages is not the same thing as having one message that's split into blocks. Just wanted to get that out there because sometimes it trips you up. Okay, we have 2 messages. And if we look at these messages, it turns out these messages, they are different. They're not identical, but they're similar. And what I mean by similar is it seems like they start with the same bytes or the same bits. In particular, the first 2 blocks are identical. So maybe this one says like, dear Bob, hello. And this one says like, dear Bob, hi, something like that. Sorry, that wasn't super creative. But maybe the first 2 blocks are the same, and then things start to change in the 3rd block. So if I take these 2 messages and I accidentally or mistakenly use the same IV, what happens when I encrypt the 2 messages? So let's give it a shot. I'm going to encrypt the first message on the left and the second message on the right, and I will look at them side by side and see how things are the same and see how things change. So here we go. The first block of plain text is the same on both sides. It's the word dear or something, I don't know. Okay. The initialization vector is also the same because we've claimed that we are mistakenly using the same one twice. Okay. If I take 2 inputs that are the same and I XOR them, what's the result? Is the same thing. So the thing that I'm passing into this block cipher encryption, same. Okay. The key I'm using is the same. Why is the key I'm using the same? Because remember, what was the whole point of this lecture? The whole point is I don't want to do the one-time pad thing where I have to change keys every time. So we are generally going to use the same key to encrypt multiple messages. So what's going into the block cipher encryption block? The same input, same XOR input, and the same key. And what do we know about block cipher encryption? Deterministic. If you pass in the same things twice, you get the same output. So this ciphertext block between these 2 encryptions, same, right? This one equals this one. Okay, same. Let's keep going and see if, right, this gets worse. Well, what do I do next? I do this XOR operation next. So I take this plain text, same. I take the previous ciphertext on both sides, same thing. I XOR the same things twice. What do I get? Same thing here. Same thing with the block cipher encryption. I know I'm saying the word same a lot, but if I take the same inputs to the block cipher encryption, and I encrypt twice, it's deterministic. I get same output again. So it seems like so far, IV reuse has already leaked that my 2 messages start with the same thing. So if this were like, I don't think this thing was invented in World War II or whatever, but if you're like in the minefields or whatever, and there are 2 messages that start with the same 2 words, okay, well now the encryption starts with the same 2 words, and whoever's looking at your messages or spying on them, they can see that your 2 messages, even if they don't know what they say, they must start with the same 2 words. You have leaked information. or the same two blocks. Okay. And so we keep going. Okay, well, this time finally something interesting happens, more interesting, which is that these two inputs are different. And if these two inputs are different, well, we XOR them with the same thing, but this input is still different from this one. So if these two are different, what happens if you take two different inputs and shove them through the block cipher? If I take two different inputs and shove them through the block cipher, the output is unpredictable. Remember, that's the point of the block cipher. The arrows could be anywhere. So if I take two different inputs and I shove them into my block cipher, then I get the case that this one and this one, sorry for super messy. Okay, I'll try to clean it up. So we know that this one and this one, they are equal because I passed in the same things. Every calculation that I did was identical between the two encryptions. Same thing over here. These two are completely equal. However, once I get to this third block, because the blocks that I'm passing in are different, it is now the case that once I pass those different blocks through the block cipher, the result of these two is like unpredictably different. Okay. And so what does that mean for any future blocks? Well, that means that if I pass this into a future block, then that future block is going to have unpredictably different inputs. I pass those through block ciphers, unpredictably different output. So all of this reasoning told us that if you reuse the IV, you end up leaking when two messages start with the same blocks. So if two messages start with all the same blocks, the CBC algorithm does the same thing for all the same blocks, all the way up until the first time something is different. And as soon as something is different, for the rest of time, the output's going to look different. Because as soon as there's one difference, I'm now passing in different stuff to the next block cipher encryption. That output will be different. Pass that into the next one, output will be different. Okay. Oh, there's a phone. Should I pick it up? It's not mine. It's okay, don't worry about it. Okay, so that's IV reuse. If it's an interesting phone, you have to come back and tell us who it is. Okay. So what we saw is that CBC mode is in CPA secure if you use it correctly. So how does it work? We split things up. We choose a random IV, we compute. And again, we haven't really talked about why it's in CPA secure, but we know that if an attacker can break this, or I guess the rough proof, I guess I will briefly sketch it out, just in case you're curious. It's not something we're going to test you on necessarily. So if you're getting bored, you don't have to totally pay attention to this. But it turns out that in security, I'll just note that a lot of proofs are what we call reduction proofs. And so what a reduction proof is the reduction proof says, if I can break A, then I can break B. So this is going to get in a little bit into CS70 stuff. So again, if you're not a huge CS70 fan, feel free to ignore this. Okay, so if I can break scheme A, then I can break scheme B. This is something that we've tried to prove a lot in security proofs. And the reason why I want to prove this is because, think way back to CS70, like dig up like in the cobwebs of your brain. You might remember that in CS70, there's this fancy thing called a contrapositive, which means that if I flip this and I invert the clauses, that statement must also hold. And if that doesn't sound familiar, don't worry about it. It doesn't even sound that familiar to me, to be honest. But basically, if you take this statement and you flip it around and you invert each of the terms, you end up getting this. So this implies this and vice versa. So one thing you could prove is I will now plug in actual things for B and A. So that was just a CS70 review thing. And not something we'll test you on in detail, but it's the sketch of proofs. If you ever go out in the real world and do these proofs, this is what you will see. Okay, so if I break CBC, AES, I'm just plugging in values for A and B here. Okay, oops, sorry, AES secure, CBC secure. Okay, so I just plugged in things for A and B here. Okay, so I can prove the security of CBC in two different ways. I can prove it in the forward direction like this. That would be like a direct proof. I would say, I'm going to assume that the block cipher is secure because it's been 20 years, no one's broken it. And here by secure, I mean the block cipher definition of security, indistinguishable from random. That's AES being secure. So I could say, if AES is secure, then I follow these steps and that shows me that CBC is secure, in CP is secure. Okay, that's one way you can prove it. But it turns out these direct proofs, they're kind of hard to come up with. It's not immediately obvious how you go from this thing being secure to this thing being secure. And maybe if you weren't really convinced by my argument of like, oh, well, hey, the attacker can't really tell this apart from random, and then they can't tell this apart, then you'd be right. That's not really exactly how people prove these things. The way that people prove this is they realize this line at the bottom, that's kind of hard to prove. So instead, they choose to use this contrapositive, which is the exact same statement in logic, but it's a lot easier to prove because now you're thinking like an attacker, and we like that. And so now you say, suppose there's an attacker out there with the magic power to break CBC. I haven't told you how they're going to do it, but suppose that, the like gods of security descend and they give Eve the magic power to break CBC. And so what we show is that Eve, with the magic power to break CBC, now has the power to also break AES using that magic power. How do they get the power? Not our problem. This statement just says, if Eve has the magic power to break CBC, then she also has the power to break AES. And if we can prove that that statement is true, then we have also proven that this bottom statement is true, and that tells us that CBC is secure. So this is called a reduction proof. It's not something we're going to talk about in any detail in this class, but if you ever go into 261, which is the graduate security class, or any like cryptography class, this is something we'll be doing a lot of. The way that we like to prove things is not directly by saying if A is secure, then B is secure. We like thinking like an attacker, and we like saying, if someone has the magic power to break CBC, they can use that power to also break AES. Once I have that statement, I flip it around using my CS70 logic, and I get the forward direction I was looking for. Okay, just wanted to put it out there if you were ever curious, but not something we will test in any sort of detail. Okay, cool, that's CBC mode. And finally, I can show you the penguin, which now looks totally indistinguishable. So looks like we did our job. Okay. Any other questions about CBC before we see our second block cipher chaining mode of the day? Yeah.
I remember reading or listening that one padding is not really effective because you need to generate keys for every single time. What makes this CBC creating keys every single time effective?
Yeah, that's a great question. So the question was, we already saw that one-time pads are not practical because you have to come up with a different IV every single time. So what makes CBC mode so practical if I have to come up with a different IV every single time? That's a great question, and I'm glad you brought it up. So remember, there's a couple of things that were really bad about having to generate random keys. One of them was that, remember that if I have an n-bit message, my message is like 1,000,000 bits long. I have to generate 1,000,000 bits of key in order to XOR every bit in the one-time pad scheme. But in this case, if my plaintext is like 1,000,000 bits long, it goes on and on and on forever. How many bits of IV do I have to generate? Just one block. So no matter how long my message is, I only have to generate this limited number of randomness. And then thanks to this chaining property, I can use the chaining property to derive more randomness, basically. So that's one nice thing, is that instead of having to generate 1,000,000 blocks of IV or 1,000,000 blocks of random key for 1,000,000 block message, I can just generate a single block and then use this chaining property to propagate that randomness through the whole message. So that saves me on randomness computation. The other thing that makes CBC better than one-time pad is that this initialization vector is public. We don't care if the attacker knows it. It doesn't affect our security. And in fact, we're okay with it being sent in public because that's how Bob, the recipient, is going to undo the randomness and get the original message back. So in one-time pad, when you generate that secret key, you also have to figure out how to secretly share it between Alice and Bob, which is really tricky. Whereas in this case, when Alice generates the IV, she can just toss it over to Bob, even if Eve sees it, doesn't matter for our purposes. Okay, great question. Okay, anything else you want to know about CBC before I'm done with it forever or until next semester? Okay. Okay, let's look at our second one. So again, we will try to design it together. And this time, instead of starting with block ciphers and working with block ciphers, trying to introduce randomness, this time I'm going to go back to the one-time pad. So I'm going to remember that one-time pad, it was actually not so bad as long as I didn't reuse the key. So one-time pad, we saw we have all these nice security properties. So like, I really want to use one-time pad. I really want to redesign it or give it a little change so that I can actually use it. What was the key problem? The key problem was that I can't reuse the key. Okay, sorry for saying key so many times. So this is our one-time pad. We've already seen it. And so I can't reuse the key. So like, what do I do? Well, I really wish that if my message were longer, I don't have to generate more keys. Or if I want to encrypt the same thing over and over again, I don't want to have to generate more keys. So where am I going to get keys from? I don't want to generate them myself, because if I generate keys myself, I have to share them with Bob over a secure channel. I don't know how to do that. That's complicated. That's expensive. So I don't want to generate keys myself. So instead of me generating random keys, I'm going to go look for something that is usable as a one-time pad key. What are the properties of a one-time pad key? It just has to be a bunch of random ones and zeros. So let me go looking for a cheaper way to generate random ones and zeros. Well, what do we know? We have block ciphers to the rescue. So remember, if the attacker doesn't know the block cipher key, what does this output look like to the attacker? Random. The attacker, from their perspective, this is just a bunch of random ones and zeros with no meaning to the attacker. So I'm going to decide, you know what? I liked one-time pads, but one-time pads had that problem where I don't know where to get them. I don't know how to generate them or where they come from. But then I remembered, well, hey, these block ciphers, these are kind of nice because this output is completely random to the attacker's perspective. So what if I combine these two ideas and I'm like, instead of getting those keys from who knows where, I'm going to try to use block ciphers to come up with a lot of different keys. So that way, instead of generating keys myself and trying to share them between Alice and Bob, I'm going to harness the power of block ciphers and that indistinguishability from random property that we saw from earlier. I'm going to harness that power to try and generate a lot of keys for cheap. And if I can generate a lot of keys for cheap, maybe that one-time pad that was so impractical, maybe it's going to be more practical. Let's try it. So we already know that anytime you take something and encrypt it through the block cipher, it basically looks random. Whatever you take, if the attacker doesn't know the key, right, whatever this input is, we're going to go through that big table of arrow mappings. It's going to map to who knows where, and we're going to get some random looking output. So from the attacker's perspective, this is as good as random. And so is this. And so is this. Anytime I take anything and pass it through a block cipher, I get something that's as good as random. The attacker has no clue what any of this is. As far as they know, it might as well be someone tossing a bunch of coins and getting zeros and ones. Okay, so now that I look at this, I'm like, wait, well, if I have all this stuff that's random, maybe that's my one-time pad key. So maybe instead of coming up with a key myself, which is super expensive, I'm going to use the block cipher encryption's power to give me all this random looking junk that I could use as a key. So I'm going to do it. I'm going to say all that stuff that came out of a block cipher is as good as random. So I'm going to use that as my one-time pad key. I'm going to XOR it bit by bit with my plain text, and I'm going to get the ciphertext output. So all that I did to go from the previous slide, this slide, I'm just observing that, hey, block ciphers, their outputs are basically random for the attacker. And then I'm going to observe that if those things are random, they can be the input to my one-time pad, or they can be the key to my one-time pad. So I've taken the block cipher, I've taken the one-time pad, I've like done a mashup, and now I get this. Okay, we are almost done, because if I go all the way back here, I never actually, or maybe even here, like I never specify what these inputs are, right? So what do these inputs actually represent, or what are they? Turns out they could really be anything, right? As long as I pass in something and I encrypt it with a key that the attacker doesn't know, this output is as good as random. So I just need to put something up there. What am I going to put? I don't know. Why don't I just put, how about I encrypt 0, and then 1, and then 2? That works, right? Because these could be anything. As long as I put in something here and I pass it through the block cipher encryption, it's as good as random to the attacker. So I can just pass in 0, 1, 2, like whatever I feel like. And from the attacker's perspective, as good as random. So let's do that. Okay. So I could just pass in 0, 1, and 2, and so on. But there's still one key missing piece to the whole puzzle, which is if I stare at this scheme really hard, still deterministic. I encrypt the same thing twice, I never actually introduce randomness anywhere. So the last thing I have to do to complete my scheme is to introduce randomness, and the way that I'm going to do it is instead of just saying 0, 1, 2, so on, as the things that I'm encrypting to generate a bunch of keys, I'm going to encrypt some random number plus 0, some random number plus 1, some random number plus 2, and so forth. And if I encrypt those things, I still get random looking junk, and that random looking junk can be my key. Okay, so that was me introducing randomness. And finally, we now have something that is a one-time pad, but instead of the keys being generated each time and we have to share the keys each time, maybe now we can generate the keys for cheap. So let's take a look at what that looks like. Okay, so this introduces something totally new it's still a block cipher chaining mode, but this time it's not CBC. This time it's called counter. So I guess a couple of things I will note. The first thing I will note is that you might have noticed that the IV got like a rebranding on this slide. We called it IV previously. Now it's called nonce. And so that's just a terminology thing. For the purposes of this class, they basically mean the same thing. In real life, there are some slightly different properties of each. I think the main property is that IVs are unpredictable and nonces can be predictable. But for the purposes of this class, they're basically the same. I will also note that I think nonce stands for number used once. Not totally sure, but that's a very funky acronym if it even is one. I don't know. People come up with funny names. Anyway, that's counter mode. Now let's think about what do we do that actually makes this a more practical version of the one-time pad. So how do you encrypt? Well, we do the same thing as always. We take the message, we split it up. That's what we always do, right? Into blocks. But then, I mean, maybe you don't have to do that, but like, okay, let's say we split it up. Okay, so we split it up and then we're going to do the one-time pad thing on it. So how do we do that? Well, in regular one-time pad, Alice and Bob have to come up with that long key and share it with each other and make it secure. I don't like that. That's too much work. So instead, they're going to do this. Alice is going to pick a nonce, random number. And then she's going to say nonce plus 0, use her one and only key. This time, we're not going to use a bunch of different keys because we know that's wasteful. So we're going to say Alice picks a nonce. She computes nonce plus 0, takes her one and only key, encrypts nonce plus 0, gets some random junk. That random junk, that's part of the one-time pad key. Okay, what's next? If I need more, maybe my message is even longer than one block, then I will continue. I'll take that nonce, I will stick a 1 at the end or add a 1 to it. I'll use my same key, the same one and only key that Alice and Bob share. I will encrypt with my one and only key. And still, if the attacker doesn't know that one and only key, this output, still total random garbage to the attacker, still usable as one-time pad input. We like that. And then we keep going. If we need more, we say counter plus 2. We use our one and only key. We send it to the block cipher and get more pad. So in effect, what we've done is we've taken a single key, just one. Alice and Bob only have to share one key for all time. And by using this nonce and shoving this nonce plus counters through the block cipher, we've basically given ourselves like infinitely usable key material for use for the one-time pad. So this is just us generating lots and lots and lots of one-time pad input as much as we want, right? We can make this counter go as far up as we need to, get as much input as we want. And then after we're done encrypting all that stuff, then we take our resulting pad for the one-time pad or the resulting one-time pad key, which is all the stuff that came out of the block cipher. We XOR it bit by bit with the plain text, and we finally get the ciphertext. Okay. And what if you want to encrypt another message? Do you have to come up with a new key? Nope. All you have to do is come up with a different nonce, shove it through the block cipher encryption, get a completely different output that only Alice and Bob know. That's great. So we've taken the block cipher and used it to allow us to encrypt a bunch of, or encrypt a nonce with a bunch of random counters, or encrypt a bunch of random nonces with increasing counters, get a bunch of completely unpredictable output, use it as our one-time pad input. Okay. Now's the question, how do you decrypt? Well, remember, this thing is one-time pad inspired. So I'm going to take inspiration from one-time pads and try to decrypt this one-time pad style. Well, how do you decrypt things in one-time pad? You take the ciphertext and you XOR it with the pad again, and you get the original message back. So that means that if someone wants to decrypt, they have to regenerate the same pad and then XOR it with the ciphertext, get the original plain text back. So Bob receives the ciphertext. Bob needs to know how to decrypt. So how does Bob do that? Bob first has to regenerate the pad. How does Bob regenerate that pad, the key that I used for one-time pad? Well, Bob is going to have to take the nonce, which means Bob's going to have to know the nonce. So we have to send the nonce over to Bob. So we send the nonce over to Bob. Bob takes the nonce and follows the exact same process that Alice did to get the pad out. So how did Alice generate the pad? Alice said nonce plus 0, shove it to the block cipher. Nonce plus 1, shove it to the block cipher. Nonce plus 2, shove it to the block cipher. All of this using my one and only key to the block cipher. So what's Bob going to do? The exact same thing to generate the pad. And so that's what Bob does up here. Like, look at these two. Before, after, same, right? Like this entire top of the diagram never changed because this entire top of the diagram, all of this is just Bob regenerating the pad for the one-time pad. And then what does Bob do after regenerating the one-time pad? We take the ciphertext, XOR it with the pad that came out, and then plain text pops out. Okay. Now stare at this really hard because something is in bold. You notice that, wait, when I encrypted, I used the block cipher in the forward direction, the encryption direction. When Bob was decrypting, he also uses the block cipher in the forward encryption direction. So this is also something that trips people up. It's like, wait, how can it be that the decryption algorithm is using the block cipher in the encryption forward direction? And the reason why we're doing that is because what was the purpose of the block cipher in this whole scheme? It was just being used to shuffle bits with the key and get a bunch of random output for use with the one-time pad. So we're not using this block cipher to actually encrypt the messages. Like, look, the message never even shows up in the block ciphers. We're just putting a bunch of random stuff in, trying to get a bunch of random unpredictable stuff out, use it as a one-time pad. So regardless of whether you are encrypting or you are decrypting for CTR mode or counter mode, you're always running block cipher in the forward direction. That's what this slide says. Okay. So overall, it is just one-time pad, but instead of feeding in completely random keys, we're just going to use a single key and harness the power of nonces, harness the power of these block cipher encryption blocks to get a bunch of unpredictable looking pads. Okay, excellent. That's decryption. We already saw it. You can also write these as expressions. I'm not going to do it right now because I think the pictures actually are a little bit more helpful here. But if you write it as expressions, you will also notice that in both the encryption and the decryption, you don't actually have to use the block cipher decryption. Okay. So now we're going to go through and ask the same questions as we always do, just to make sure, is the scheme secure? Does it work? Is it fast? Let's go through and think about all those things and make sure that everything checks out. So first question is, well, can we parallelize? And again, parallelizing is nice. We like to split up the work so that we can do things in parallel. We like encryption to be fast. So let's think, can I take a message and say, you encrypt the first half, you encrypt the second half, and then we put it all together at the end? Well, what does someone need to know to encrypt some part of the message? Well, they just have to know the nonce, which we know at the beginning of encryption. And they have to know all the counters, we know those. And then we just shove those through the encryption and we encrypt every bit one by one. Okay, that works out. And so turns out there's no like dependence here. Remember in CVC mode, the thing that broke parallelization is the fact that we had to wait for the person before us to finish computing ciphertext so we could take their output and chain it into our input. But in this case, we don't have to wait for any of the output. All that we need to compute the output is just the nonce, which we already have, and the plain text, which we already have. So the answer is yes. I guess we didn't even bother explaining it, but I just did. Okay. So the answer is yes, because every block basically kind of works in independence. There's no dependence on previous blocks. We don't have to wait for anybody else to compute something and give it to us. We have all the tools we need to make the computation right now, so we can parallelize. We need the nonce, we have that. We need the counter values, we have those. We need the plain text, we have that. And decryption, kind of the same thing. We have the nonce, we have the counter, and we have the ciphertext. So we have everything we need to decrypt. We do not have to wait for someone else to give us something in order to decrypt the message. Okay. That's all that this slide says. Let's think about padding. Just like before, what happens if someone has a message that's like 2.5 blocks long? Well, let's give it a try. So, well, let's try it. So what happens if I have 2.5 blocks? Well, I have a full block here. We know how to deal with full blocks. Full blocks are easy. We take the nonce, we shove it through block ciphers. The block cipher outputs exactly one block of data, and we do the XOR, and we're set on block number 1. Same thing with block number 2. We run the nonce and the counter through the encryption, get a full block of random garbage padding bytes, take those random garbage padding bytes, XOR them with our plain text, get a full block of ciphertext. Things are looking pretty good so far. And now we come to the place where there's half a block of plain text. So what do? Well, we can still take the nonce and the counter. We can still shove it through the block cipher encryption. And what do we get on this side? So I will maybe even draw this more. I'll draw this a bit larger just so you can see it. So what comes out of the encryption block over here? N bits of output. Why is that? Because block ciphers are fixed size. They give you exactly N bits, no more, no less. Okay. What do I want to XOR the N bits with? I want to XOR the n bits with my plain text, but my plain text is not that long. Maybe it's like n over 2 bits or something, right? That's my plain text. It's not as long because I have 2.5 blocks. This last block is a bit shorter. So on first glance, you might be like, uh-oh, how do I bitwise XOR n over 2 bits with n bits? Seems like I can't. But there is one thing you can do, which is you can say, out of these n bits of padding, remember, what are these n bits? These are like random ones and zeros that you can use as a one-time pad. You could just say, you know what? Those n bits, I don't need all of them. I just need the first n over 2, and the rest of them, I'm just going to throw away. I don't need them. Because what am I doing? I'm doing one-time pad. And for one-time pad, all I have to do is take every bit of plain text and XOR it with a random bit of the pad. So I'm going to say this n bits. I don't need all these n bits. I'm going to just say, just give me the first n over 2 bits here. Okay, that's a funny 2. Just give me the first n over 2 bits. I will XOR those with p, and I'll get n over 2 bits of output right here. So I'll throw away the stuff I don't need. That works perfectly. So when I'm encrypting stuff, if I get too much output because my input is not a multiple of the block size, I'll just throw away what I don't need. I know with one-time pads, every bit is XORed independently. So if I get stuff I don't need, forget it, right? Don't need it. That's one way to reason through this. Another way to see that padding wasn't needed for encryption is to note that this plain text, which is like a half block long, that's my problem block. I don't like this half block because it's hard to deal with. But I'm never passing the half block through the block cipher. In CBC, where did the problem come up? The problem came up when I took my half block and tried to shove half a block of data through the block cipher. It would not accept it. But in this case, if I look at this diagram, this half block, it never goes through the block cipher. It's on the other side. I'm only doing XOR operations on it. So I can just throw away the bits I don't need from the block cipher output, and I'm all set. Okay, that was this line. And you might have a question, which is, well, wait, what happens to the person trying to decrypt? Well, now the person trying to decrypt, they get 2.5 blocks of ciphertext. They get my full block here, just like before, and then they get a half block here. So what does Bob do when Bob gets a half block of ciphertext? Well, same thing. Bob takes the nonce, and Bob takes the counter for this particular block, shoves it through the encryption scheme with some key. We've already seen all this stuff. And what does Bob get on this side? Bob gets n bits of pad. Okay, what does Bob need to XOR this with? What have Alice, provided to Bob? I provided n over 2 bits over here. So what does Bob do? Bob does the same thing. Bob says, well, Alice gave me n over 2 bits, and I have n bits of padding here. So what's Bob going to do? Bob's going to do the same thing. Throw away whatever he doesn't need, keep the first n over 2. So Bob's like, I don't need all n of this stuff. I'm just going to use the first n over 2 bits. Okay, and then I will take the first n over 2, XOR it with whatever Alice gave to me, get my output. So Bob's decryption works great too. So the way that we deal with padding in one-time pad, the way that we deal with padding in CTR mode is we don't. All we have to do is throw away the parts of the pad that we don't need. And Alice and Bob can both do that. Okay, that's padding. So we don't need to actually add a bunch of extra bytes after our message to make sure it's the proper length. CTR mode works with any length, which is kind of nice. Okay. Finally, we deal with security. And again, there is a reduction proof somewhere in there where you can say, oh, if I break CTR, I break this other thing. We're not going to do it. And we will just roughly say, right, we've already kind of felt that this thing is basically one-time pad because all of this block cipher output is unpredictable. That's kind of how I like feel intuitively that CTR mode is secure, even if we're not going to go through a whole proof of it. But again, there is one key assumption you have to make. And the key assumption you have to make or else is that nonce had better be randomly generated and not reused. Because what happens if you reuse the nonce? Bad things happen. There's also one tiny little nit, which is that you can't encrypt so much stuff that the counter like rolls back to 0. But in practice, that doesn't really happen. So that's what that bullet point says. Okay. So what happens if you reuse the nonce? We can do the same. We can do the same analysis as we did for CBC mode and think, well, what happens if you take 2 messages and encrypt them with the same nonce? If the 2 messages are identical, we already know that the output's going to be totally identical. It's deterministic, no randomness. But what if my 2 messages are different and I reuse the nonce? Well, I could go through the whole analysis, but I could also just remind myself that what does the nonce do in the picture? The nonce, all that it does is it tells me the output of the one-time pad that I'm using, right? The thing that I'm XORing with the plain text of the ciphertext, that is the output of the block ciphers. That's what the nonce is for. So if I reuse the nonce, same nonce both times, then I guess these are, encryption and decryption. But if I reuse the nonce, then this output's going to be the same every single time, right? And if I use the same block cipher outputs every single time, and I XOR it with different plain texts, what am I really doing? I am reusing the key to the one-time pad. That's what I'm doing, because the nonce is determining what my one-time pad key is. And if I reuse the nonce, I get the same one-time pad every single time, XOR it with different plain text. I'm basically doing two-time pad, as we saw from last time. And we already saw from last time, what happens if you reuse a one-time pad? It's really bad, because now people know a lot of things. They know, like, what's the XOR of your two messages. You leak all sorts of information. So if you reuse the nonce in a one-time pad, things go really wrong. In fact, I would argue they go more wrong than in CBC mode. In CBC mode, people find out if you have the first couple of blocks the same. In CTR mode, they find out way more. They find out exactly what the XOR of your two messages are. That's kind of bad. Okay. And in practice, usually knowing the XOR between two messages can actually give you the whole plain text. So CTR mode, if you reuse the one-time pad, pretty catastrophic. Okay. And we already saw the penguin. Again, totally random, good for us. That's assuming we don't reuse the IV. So just to hammer it home and like finally follow up on this infamous slide from last time, what was the mistake that they made, you ask? So they were using some Python library to encrypt stuff, and they had to call the CTR function. So somewhere in Python, there was like a library called crypto or something, and they were like crypto.ctr encryption or something. And for some reason, that CTR library asks you to pick an IV for them. So you all being, good 161 students that you are, what are you going to do? You're going to pass in a different IV every single time. However, I guess these 61A folks, they didn't think of that. And so they just didn't specify the IV, left it blank. And so what did the Python library do? I guess they assumed maybe they would, that, the random IV would be added for them, or maybe they just saw the argument that said like IV or nonce. They were like, what the hell is this? I'll leave it blank. I don't know. But for some reason, they didn't specify an IV. And for some reason, the crypto library decides if the user doesn't give me an IV, I will pick 0. I don't know if that's what crypto library should do, but that's what the Python one does apparently. And so they ended up using the same IV to encrypt multiple exam questions, and ends up being like reusing a one-time pad. So a student gets to know what the XOR of two questions is. And it turns out in real life, it's not that hard to pull that apart and figure out what the questions themselves are. So now you know what they did. In terms of what mistakes they made, let's say as 161 students, they probably should have known what IVs were. So that's their first mistake. But I would also say, like, as a Python library, it's kind of weird to me that the library just defaults to 0. So I guess it's a matter of what you think. But ultimately, don't be a slide in our lectures, and make sure to use different IVs. Okay. Great. And as we said from before, right, like, don't build your own crypto. If you do, even a little tiny mistake, like forgetting to specify IVs, could destroy your system. So yes. Okay. So you don't know how to do it. I don't know how to do it. Unless your name is like David Wagner, two-fish genius, you probably don't have the skills to do it. Okay. And that's okay. That's not a bad thing. Crypto is tricky. Okay. Great. So we already talked about IVs and nonces, right? We already said that they basically are the same thing. In real life, the terms mean something slightly different, but for the purposes of this class, we will just say nonce or IV interchangeably. It's okay for us. And we already said that in some schemes, reusing IVs is kind of bad, like CVC. In some schemes, reusing IV is really bad, like CTR. So depends on your scheme. You can reason through what happens if you mess up. In some schemes, messing up is kind of bad. In some schemes, messing up is really bad. In general, though, the way to not mess up is to pick something totally random, totally unpredictable for IVs and nonces, and you're all set. Okay. And so another problem is, well, maybe you kind of felt this, like thinking through this stuff was not easy. We talked it through together, but like having to think through what happens if you reuse the IV, that was not really easy. We had to think, okay, well, this output's the same, and then this output's the same. And if I do this, I get like a one-time pad reuse, right? That wasn't the easiest thing in the world to do. And like, I don't know about you, but I didn't find it the most fun thing in the world to do either. And so in real life, you basically have two options. You can be the 61 ATAs who had to sit down and think really hard about, wait a minute, when I reuse my IV, now I have a 2-time pad, and now people can, people know the XOR of my exam. And if someone knows the XOR of the 2 exam questions, can they figure out the exam? You can be like them and think about that really hard. Or one option is you can just use different IVs. And if you use different IVs, you never have to think about this. So I like that solution. It's up to you. You can either think really hard about what happens if you reuse IVs, or you can simply not reuse them and not think about this. Okay. On exams, you will probably have to think about this, but once you're done with this class, go with solution B, right? Use different IVs, don't have to think about it. Okay, great. And so, both of these schemes, they work, they have nice security properties. And so, which one do you like better? Well, it's a matter of opinion. We don't have a favorite. Maybe you have a favorite. Maybe when you go out in the real world, you have a favorite. And so there's different trade-offs depending on what you value. And so what we say on this slide, which is a matter of opinion, it doesn't have to be what you say, is, well, if you really need to encrypt stuff fast, you're like, I have a mountain of data that I must encrypt instantly, then maybe CTR mode is what you're going for, because CTR mode has that nice property where everything is parallelizable. So maybe you like CTR because you really want to parallelize stuff and encrypt stuff fast. Maybe you're someone who's really paranoid about security, and you're like, what if I reuse the IV? Or what if I'm handing this mode of operation to someone who really doesn't know what they're doing, and I really want to make sure that even if they mess up, my scheme doesn't break? Then maybe you're a fan of CBC, because we already saw CBC leaks less information if you mess up. So which one do you like better? It's kind of a matter of what you prioritize, what application you're using it for, but both of them, they work. They're both used a lot in practice. So which one you like better is a matter of opinion. That's what this slide says. Okay, great. But again, do be careful with both of these, because again, if you reuse IVs, like this happens in real life, 61A had it, other systems in the real world have happened before, so not good news. Okay. There are also other modes. So these are not the only 2 out there. There are lots of others. Some of them are provably secure, some of them aren't. So here's a bunch of other ones. And for all of them, you can ask yourself these questions. So, if you're really bored and you want to go analyze these trade-offs, you can do that. All of them have the same properties of, is this padding necessary? If I mess up and I reuse IVs, how bad is it? Is encryption parallelizable? Is decryption parallelizable? These are all things you can ask yourself. It's nice practice for exams and so forth. So I'm not going to talk about these now, but you'll get a chance to practice these in like homeworks. If you ever go to like past exams, we have lots of schemes that we make up. So, these are all schemes that exist out there. And you can see they're all kind of modeled off the same idea, which is I have these block ciphers, and I'm going to use the block ciphers over and over to encrypt longer messages with the same key. Okay, so you can analyze the trade-offs. I won't right now, but if you're curious, we can talk about it. Again, in homeworks, you'll see them. There's the solutions if you're ever curious. Okay, there are more schemes that you will see, basically. So these are the 2 that we are going to talk about, but just know that there are more out there. Okay. In the last 7 minutes, I want to remind you that I know this is like, like days ago at this point, but maybe you remember that when we started this lecture long time ago, remember how we were in this square? It was like slide number 1. Because we're in this square, for the last week, we have only been thinking about confidentiality. So all the things we've been thinking about, the ultimate goal was to stop Eve from reading our messages. That was all we cared about. And for all of this time, we were not actually worried about it. And it was intentional that we were not thinking about other things like, can other people mess with my messages without being detected? So the last thing that I want to show you and warn you about is that even though we just went through all this trouble to build a scheme that is fully confidential, that only satisfied the confidentiality security definition that we talked about. We've not talked about integrity or authenticity. And it turns out that this scheme by itself does not have authenticity or integrity. And so what that means is that somebody could change my message while it's in transit between Alice and Bob. And when Bob decrypts, he will not know that it has been tampered with. Okay, so I'll show you an example, but just know that this whole scheme, it was designed for confidentiality and only confidentiality. We did not design it for integrity or authenticity. It was not built for it, right? We were not trying to build a scheme that gave us integrity. We were trying to build a scheme for confidentiality. We did it, but just want to remind you that building something for confidentiality does not mean we get the other properties. Okay, and here's an example of how. So this example, it's a little bit contrived. Maybe you won't be super convinced by it, but just know that these things are possible. So Let's say Alice sends a message to Bob. So Alice takes the message, pay Mallory $100. And Alice encrypts it with CTR mode, sends it over to Bob. So how does Alice encrypt this thing with CTR mode? Remember, she takes the nonce and the counters, she plugs those into block ciphers, gets as much one-time pad output as she needs. And this is the one-time pad output that Alice generates. And then she does the one-time pad XORing. That's how CTR mode works. And I get some output. So whatever pay Mal $100 was, we encrypt it. And this is the thing we're going to send to Bob. Okay. So this thing, Alice sends it over. Now it's floating over in the insecure channel. And we already know that this thing has confidentiality. Eve, as much as she tries, will never know what this message says. Even if Eve has that power of tricking Alice into encrypting messages, she will never know what C is. That's great. However, suppose we're not dealing with Eve, we're dealing with Mallory. So maybe Mallory's like, I know the message says pay Mal $100 and I want to get more than $100. So this is an assumption we're making. Even if you don't make this assumption, this attack is still possible. But if we assume that Mallory knows that this message says pay Mal $100, because maybe she does, right? Maybe she knows that this message is coming along at some point. Well, then one thing she could do is she can try and change what this message says so that when Bob decrypts it, Bob gets a different message like pay Mal $900. That would be bad. And so the way that she can do it, I'm not going to walk through it, the whole derivation, but it is here for your reference. What we can do is we can say this byte, we already know from before that one-time pad works on each byte one at a time, right? It's like character by character. So I know that if I want the message pay Mal 100 to change to pay Mal 900, I just have to change that single byte that corresponds to the digit 1 and make it say 9. Okay, so how does she do that? Well, turns out derivation looks something like this. I'm not going to talk through it in too much detail, but if Mallory knows the message, because we assume she does, and Mallory knows the ciphertext, which she does because it's floating over the insecure channel, Mallory can solve for what the block cipher output was. And if Mallory can solve for what the block cipher output was, then she can use that block cipher output, which is the pad, and encrypt the number 9 herself. So she can run her own XOR with the number 9, with the digit 9, and get some modified C prime. So she can take that bit of C, she can do some fancy calculations, swap it out for a different byte. Now she's got C prime. Now when Bob decrypts this, Bob now sees $900. Okay, so that's the rough attack. And so what we see here is that Mallory was able to change the message and Bob was none the wiser. He had no idea that the message changed. Okay, and Mallory did not have to know the key in this case. And if you're not convinced, you're like, I don't like this. I don't think Mallory should know that the message said pay Mal $100. Well, that's okay. Even if Mallory didn't know what the message said, she can still do this, right? She can take the ciphertext, she can change any bits that she likes. And when Bob decrypts, Bob has no idea that the message has been changed. Maybe the message looks kind of unintelligible now, or it looks like garbage, but Bob has no way to prove to himself that Alice wasn't intending to send it. So if Bob decrypts, maybe he gets garbage, maybe he gets pay Mal 900, maybe he gets something else entirely, but whatever Bob gets, there is no way for Bob to prove to himself, did this come from Alice or did somebody tamper with it in transit? Bob doesn't know. So we still have to solve this problem. We're going to do it next week, but that's it for the confidentiality block. We already talked about CBC as well. This is an attack that you will see in homework 3, which is that CBC, it's more complicated, but you can also tamper with messages in CBC. Okay, so these are the two things we saw today. And in summary, right, we finished the top left block. We talked about ways that Alice and Bob, using a single key, can encrypt multiple messages using the power of block ciphers and chaining them together. We saw that we had to introduce randomness. And before you go, the last thing I will say, I repeated it last time. I will repeat it one more time today. We introduced randomness and randomness gave us in-CPA security. However, introducing randomness does not guarantee in-CPA security. You have to use it in a clever way, which we saw today. So do know that if you have no randomness, it's not in-CPA secure. We already saw how deterministic schemes are not secure. If you do introduce randomness, maybe it's secure, maybe it's not. It's only secure in a limited number of ways if you use it cleverly. But on exams, don't be tempted and see like, oh, it says the word random. I'm going to start bubbling in the secure box everywhere I see it. Right? Just because randomness has been introduced does not mean we have security. Additional analysis is usually needed. Okay, so I wanted to repeat that one last time just to remind you. But that's it for today. So next time you come back, we will talk about the other blocks. So next time we'll come back, not the other box, but the other squares. So the next time we're gonna go through this block and talk about integrity. Okay, see you next week. Okay. Questions in Zoom chat. Is nonce public? Yes. All right. See y'all next time.